In an earlier lecture, we talked about how the initial pulse of plants invading dry land in the first half of the Paleozoic was permitted by the development of an ozone layer and also potentially driven by a global cooling event in the Ordovician, which caused sea levels to drop and global climate to dry, thus creating an extra impetus for the proto-plants to become better at dealing with life with less water. Most of that discussion hovered around events taking place in the Ordovician and Silurian, which together with the Cambrian make up the first three periods of the Paleozoic. In this lecture, we turn our attention to the second half of the Paleozoic, which is also characterized by dramatic climate shifts driven by biogenic and abiotic factors and forcings. The periods to pay attention to here are the Devonian, the Carboniferous, and the Permian. The Devonian started out warm and quite wet, with seasonal flooding that created warm, shallow inland seas that were highly productive. We'll see in the next unit that these largely freshwater habitats were where the evolution of vertebrates took an important new direction. But over the course of the Devonian period and into the Carboniferous, things got progressively cooler, thanks to the drawdown of atmospheric CO2 by the rise of land plants. Along with cooler, we also get drier because of less evaporation occurring off of a cooler ocean surface. Dry seasons got progressively longer, and for both plants and animals, selection favoring the ability to persist under greater drought stress was an important factor shaping their evolutions. The Carboniferous was a period with peak O2 as well as lowest CO2 in the Earth's history. In tropical latitudes, there was an atmospheric convergence, concentrating much of the Earth's precipitation into a narrow belt of cool, ever-wet forests. I mentioned these in an earlier lecture. Intense photosynthesis there allowed the carbon dioxide drawdown to continue even as the polar ice caps expanded. But then in the Permian, the movements of plates pushed the continents together into a supercontinent, Pangaea. Loss of those cool, carbon-sequestering forests resulted in a reversal of the drawdown, and things did get warmer, but not necessarily wetter, at least not for large swaths of the Earth's land area. Atmospheric moisture comes from the evaporation off of the oceans, and so while the warmer temperatures would mean more evaporation, we have to consider where that water would be falling. Remember, Pangaea is a continent the size of 3 Asias put together, and so while the moisture-laden air masses would be providing rain for the coastal areas, the vast interior of the supercontinent would have largely become desert, or at least very arid. You see exactly this happening today in Central Asia, where the vast Gobi Desert is one of the driest places on Earth. Now remember how we noted that those alien forests of the Carboniferous consisted of things like giant club mosses and giant horsetails and ferns? Well, the forests of the Permian were mixed in having a new form of tree, seed plants, as well as those giant non-seeding vascular plants that dominated the forests of the Carboniferous. As we'll see in the next video, seed plants had characteristics that gave them further advantages in adapting to terrestrial life that may have become even more important with the drought conditions that prevailed on much of the Pangaean landmass during the Permian. The end of the Permian period also closes the Paleozoic era, and this coincides with the great dying of 252 million years ago, the largest mass extinction documented by the fossil record. While there could have been many causes contributing to this cataclysmic period of death and destruction, the most important cause was an enormous pulse of volcanic activity that resulted in something like 3 million cubic kilometers of magma rising up through the crust and creating flood basalts spreading to cover an area the size of Europe. These basalts are located in western Siberia, and hence we typically identify them as the Siberian traps. The severity of the impact of these eruptions on life was exacerbated by the fact that as the magma rose up to the surface, it passed through massive coal deposits, resulting in its combustion and a rapid release of carbon dioxide into the atmosphere. This parallels the current pattern of rising carbon dioxide resulting from the combustion of fossil fuels by the human population. In the next video, we'll address the evolution of seed plants, which originated in the Devonian, diversified through the Carboniferous, and saw one superclade, the gymnosperms, coming to light in the Permian fossil record. Note that the flowering plants, angiosperms, they don't hit the scene until later in the Mesozoic.